All right, so we're looking at conditional probability, and the idea here is that we want to be assured that something has happened, and then find the probability of something else as a result. Okay. So we have some notation here that A with a vertical line and then B. These are A and B are two events. And this is just written as A given B. Okay? Now, one rule, and this is actually how it shows up in your IB formula booklet, is that it just says independent events, and then it says a variation of this formula. It actually says the probability of A and B equals the probability of A given B times the probability of B. Okay? That's for independent. Well, this is for all events. Okay? This is for all events. If they are independent, then it says the probability of A and B is the probability of A times the probability of B. Okay? So you'll notice here, if A and B are independent, the probability of A given B is simply the probability of A. In other words, B happening has no impact on the outcome of A. Very simple example. If I roll 2 dice, what I roll on the first die is not going to impact the probabilities of what I'm going to roll on the second die. Okay? If I roll a 3, it doesn't make it any less likely that I'll roll a 3 the second time. Okay? I still have a 1 in 6 chance. So because those are independent events. Independent events are events where the occurrence of one has no impact on the probability of the next one. Okay? Now, the formula, and I should clarify this here, all events and independent events. Okay. Now, the formula here in the blue box is the one that you're probably going to use the most as you are working on problems here. The probability of A given B is the probability of both divided by the probability of the given. That's an easier way to remember it than just the notation. We have the probability of both happening divided by the probability of the given happening. Okay? Now, we've talked about this a little bit. Let's go ahead and look at an example or two. Okay? Here we have a Venn diagram. Venn diagrams are super helpful when we are working with probabilities because we're able to visualize what's going on. Okay, so here we have this box and it has 2 circles in it overlapping. So it says here we have a group of 30 people, 20 of them enjoy soccer, 18 enjoy football, and 3 don't like either one of those sports. Okay? Now, before we get to probabilities, let's set up our Venn diagram here. Okay? So let's say that the purple is soccer and the yellow is football. Okay. Where could we put these 30 people?
3 go on the outside.
Okay, 3 are going to go on the outside of both circles because they do not like either sport. Okay? So that means that the numbers inside the circles have to add up to what? 27. Okay? The numbers there are going to be three different numbers here. The number just in S, the number in the intersection, and the number in F. That has to add up to 27. Okay? So how are we going to figure out what goes in what area there? Okay, so here's the thing. The total in this circle has to equal 20, right? So how many go here and how many are going to go here? You're right, they have to add up to 20. If you want, you could make this like x, y, and z. And yeah, x plus y has to equal 27. Or I'm sorry, not 27, 20. And we already said that all three of those numbers have to total how much? 27. Okay. What else do we know? What about the football players? Or the people who like football?
Y and Z equals 18.
Yeah, y and z would add up to 18. Now, do you have to write a system of equations like this? No, there is a logical way to figure this out, but do you see how we could figure it out though now? Come on, be brave. Ideas? Thoughts? What?
We can put 20 into x plus y plus z and be 20 plus z equals 27.
Oh, yeah.
Yeah.
Yeah, that's a great idea. Take this x plus y and put it in here for x plus y. So 20 plus z equals 27. Perfect. So we know now that z is 7. So there are 7 people. How would I describe those people in relation to my situation? There are 7 people who
Only enjoy football.
very good. They only play or only enjoy football. Okay, so they like football and they don't like soccer. Okay, very good. Now, once you get one of these numbers, the rest of this is pretty simple to find. So now what's y?
So 7, z is 7.
Z is 7.
18 minus 7 equals 11.
Very good. So now we know there's 11 here. That means there's 11 people who enjoy both sports. Okay. And then that means how many are in X?
9.
9.
9, yeah, because we know that the total people who like soccer is 20. Okay? So good. You figured that part out. Another way to figure this out logically is if you look at how many people enjoy soccer and football and you add them together, you get 38, right? And if there's supposed to be a total of 27 people in those circles, 38 minus 27 is 11. That means 11 of them must have gotten counted twice. Okay, so there's a way you can figure out your intersections. That's why I said the equations are great if you're more analytical and you like, having nice equations to work with. If you're a more logical type of person, thinking it that way is good as well. I don't care how you think it through, however you can figure it out, okay? It's just kind of like a little puzzle. All right, so now we've got to figure out these different probabilities, and I want us to use proper notation as well. So if I were trying to find the probability that someone likes both sports, this would be the probability of, and how would I express that?
A equals
One.
Okay. We're using S for soccer and F for football, so this would be,
S.
okay. And when we want both, that's intersection, right? Okay. So it's that upside down U for intersection. And then what would the probability of this be?
11.
Yeah, 11 over 30, okay? You don't need to convert that to a decimal or a fraction, just leave it, okay? So we have 11 and 30 chance of finding somebody who likes both sports, okay? What about at least one sport? What are we finding the probability of there? Either soccer or football, okay, or both. Yeah, at least one, soccer or football or both. So what do we use for that? Yeah, the U for union, okay, soccer or football. And what's our probability there then? Yeah, that's 27. There are 27 total people out of the 30. That you should at least, if you can reduce the fraction, you should reduce the fraction. That's 9 out of 10. Okay? So 90% of these people like at least one of the sports. Okay? Now, here's the new part, okay? What's the probability that someone likes football given that they like soccer? And we're going to do this both two ways. One, using the Venn diagram, and then another way using our formula, okay? If you have a Venn diagram, given probabilities are super easy, all right? But we're finding here the probability of football given that they like soccer, okay? Now, especially when you have a Venn diagram, you can look at that given as kind of changing the scenario that you're looking at the probability of. We don't care about anybody else. All we care about are the ones that already like soccer. So how many people are that?
20.
Is that? That's 20. So we're only going to take this out of those 20 people who like soccer. So now, out of those 20 people, how many people like football? 11 of them. Okay? If you look in that circle, the soccer circle there, you can see that 11 liked football out of the 20 that liked soccer. Okay? So if you have a Venn diagram, you don't need to use the formula if you just think about what that given is doing for you. Okay? Now, again, there will be cases where you have to use the formula, and also sometimes if you just like using formulas rather than logic, you may choose to do it this way as well. But we can do the probability using our formula, the probability of football given soccer, which we know already know is 11/20ths, but this is how we would find it. It's the probability of somebody liking both divided by the probability of someone liking the given. So that's soccer. That's our formula that we just saw on the previous slide here. Okay, the probability of both divided by the probability of the given. And remember, the second one is the given. Okay? So, as we figure this out, the probability of both we figured out up in part A, that's 11 out of 30. Okay? The probability that someone likes soccer would be what?
9 out of 30.
Not
Or,
9.
sorry, 20.
The full 20. Yeah, the 20 out of 30. Okay? Okay? And you can even see it here. 11/30ths divided by 20/30ths. I can reduce that fraction by 1/30th on the top and the bottom. So that cancels out. And I get our answer 11/20. Okay? So here you can see how this works. Okay? Both logically and analytically with our formula. Okay? Any questions about this part? Okay, so that is the easier type of problem to work with when we're dealing with conditional probabilities, okay? It gets a little more challenging in cases where we have to use the formula, and especially in cases where we have a number of different options. So let me show you an example of that. When we have to do a tree diagram, okay, and actually you don't necessarily have to, but it is very, very helpful, and especially at our level, I know I can't visualize all the different details that I have to in my head, so even for me, I like to draw a tree diagram in situations like this. So we have two different situations here. We have a weatherman's prediction, what he says is going to happen, and then we have the reality, okay? Now, these may or may not be independent of each other. Hopefully they're not independent of each other, because that would mean our weatherman is just like totally guessing, which, I don't know, you wonder sometimes. But here's what we have. A local weatherman predicts rain 30% of the time. So on my first branch of my tree diagram, I have rain and not rain. Okay? So we have a prediction of rain and a prediction of no rain. Okay, so I used that R prime there. So he predicted it 30% of the time, or 0.3. Which means he's predicting that it will not rain how often?
70%.
70%. Okay? So 70% of the time he's saying, nope, it's not going to rain. Okay? Now, here's the reality. Depending on, or regardless of what he predicts, it's still possible that it could rain in reality or not rain. So to use a different variable, we'll use W for wet. Okay, so it's going to be wet or it's not going to be wet in reality. And it's going to be wet or not wet in reality. Okay? So here's the other two things that we have. When he predicts rain, so when he predicts rain, he is correct 80% of the time. So when he predicts rain, 80% of the time it actually does rain. So this would be 0.8, which means he's also wrong 20% of the time. Okay? Then we have the other situation where he predicts that there is no rain. When he predicts there is no rain, he is correct 75% of the time. So right here, no rain is 75% of the time that he's actually correct. So that's 0.75, which means when he predicts no rain, it actually does rain 25% of the time. Okay? Now, we have this nice tree diagram, but what good is it? Okay, well let's look at this and see what we actually can find now. Alright? So here our probabilities that we can use, the probability of a prediction of rain and actual rain is going to be 0.3 times 0.8. Okay, anytime you have a tree diagram like this, you're simply going to multiply 0.3 times 0.8, which would be 0.24. Okay? And then a prediction of rain followed by no rain is 0.3 times 0.2. So 0.06. Okay? Is everyone following what we're doing here? Okay? So at the end of each branch, you may not use them, but I would recommend just getting into the habit of going ahead and writing these probabilities at the end of each branch. So 0.7 times 0.25. Also, we don't want to round at all, okay? So 0.7 times 0.25, what would that be? 140, 175, so 17.175. Okay. And then 0.7 times 0.75, that would be 0.525. Okay. Now, here's kind of the moment of truth, and here's how you can make sure that you did everything correct. Those are all the possible outcomes, right? So what should those all add up to?
1.
They should all add up to 1. Okay? So 0.24 plus 0.06 plus 0.06 is 0.3 plus 0.175 plus 0.525. Okay, so that's 0.3, and that's a 0.8, or no, 0.7? Yeah, so it adds up to 1. Alright, so we know we did that part right. Okay? So now let's get to the probabilities that we're asked to find here. Okay? And this is the part that can get a little bit tricky because people forget about stuff, alright? So, we want to find first of all the probability that it rained. Okay? So in our scenario, we're finding the probability of W. Okay? Here's what people forget. There are two different scenarios in which it could rain. it could rain after he predicted rain, or it could rain after he predicted no rain. We need to account for both of these. Okay? So, it rains after a prediction of rain, plus it rains after a prediction of no rain. So I need to add those two probabilities together. Those are two mutually exclusive possibilities. Okay? He either predicts rain or he predicts no rain. There's no overlap there. So those are mutually exclusive. So I'm going to add those together. Okay? So I get 0.24 plus 0.175. And we find that it actually rains 41.5% of the time. Right? Yeah. 0.415. So 41.5% of the time it rains.
So maybe not count.
Okay? Does everyone understand how we got that?
Yeah.
Okay? Now, part of the reason why we figured that out is because our next question here, find the probability that the weatherman predicted rain given that it did not rain. Okay?
Oh, so you have to.
So let's think our formula through here first.
Oh, don't you have to divide?
We have to divide.
Because it's the two, it's the, given that he, so you have to add the two in which it didn't rain,
Mm-hmm.
and that's on the bottom. And then the top is the one where he predicted it, but it didn't rain.
Yes. So there's the probability of both. He predicted it and it did not rain, divided by the probability of the given. It did not rain. Okay? Now, to find the probability it did not rain, you could simply look over here. Here it did not rain and here it did not rain. So that's 0.6 plus, or sorry, 0.06 plus 0.525. So that's a 0.585. And that's our denominator, 0.585. The other way you could do it, since we already calculated the probability it would rain, how do I get the probability it doesn't rain from that?
Times each other. Like use the probability of rain times the probability of the bottom, like this.
This one?
No, the 0.585.
Oh, okay. It's actually simpler than that. If I know that this is the probability that it will rain,
Oh, then you just subtract from one.
the probability it's not going to rain is 1 minus this, right? That's the complement. Alright, so if it rains 41.5% of the time, it's not going to rain 58.5% of the time. Okay? So you can just subtract if you've already figured this out. Or, like we did, you could just come up here, what's the probability it doesn't rain, and add those two numbers together. 0.06 and 0.525. Okay? But notice here now too, we need the probability that he predicted rain, but it did not rain. And since we already labeled it, that's easy to find, that's this 0.06 right here. Okay? So, 0.06, okay? And then you can use your calculator to figure out what that would actually equal. Okay? Or if you like reducing fractions, you could do it that way too. Make it 60 over 585. Which, if I reduce it by 5, it's going to be 17 plus 12 over 117, which is 4 over 39. What does that come out though as a decimal?
10.2.
10.2.
What is it?
10.3.
10.2%.
What are the decimals?
Oh, 0, 1, 0, 2.
102
5.
5. So
3.
you should round it to
3.
yeah, 0.103. Hey guys, that's a big deal because you can lose accuracy points on the exam if you don't round properly. Okay? Now, when in doubt, just go ahead and give more decimal places. Alright? But just be careful with the rounding there because they would take off if you put 0.102. We don't want to lose points that way. So. Alright, any questions about that? These are kind of cool problems. They're complex, but they're kind of neat. So
They were a lot worse the first time we learned them.
yeah, that's why I wanted to cover it again completely because this is the kind of thing that you like seeing it again is helpful.